screen. That is perfect. So hi, as Sujit already said, my name is Gabriela Paulus. I'm going to be the one presenting today. And usually during these meetups, we have 2 to 3 presenters. However, you get in the OSTHUS special in the cloud as an accelerator for Bioinformatic Insights. So it's just going to be one presentation. So we might be finished a bit early. That means we can get a lot more questions from you. We can get into a lot more detail. And yeah, for now, I'll be jumping right into the presentation. So you can see the presentation here up top. As I heard from the introductions, we have quite many backgrounds. So I think we have physicists, we have some medical backgrounds. I heard molecular biology, so a bunch of different backgrounds and people. So I'll try with this presentation to cater to everyone. We'll start at the very beginning with the first chapter, the introduction, what is the cloud? And I'm sure many of you have worked with the cloud or have knowledge of the cloud already. So for you, this introduction can serve as a small refresher. And for everyone else, just to bring everyone on the same page so you all know what we're talking about and what the topic today is. Now, after this introduction, we'll jump into the second part, IT architectures. And here I'll be explaining first the general IT architectures. So how a cloud architecture is actually set up, before then jumping into a few more bioinformatics specific architecture types and explaining why they're useful and how they can accelerate our findings and our results in bioinformatics, especially in genomic analysis. After the IT architectures, I'll be briefly shown a tool that's called NextRain. And NextRain is a tool that creates interactive phylogenetic trees. So first, we will see this tool on the NextRain website, before then moving on to see how it can be hosted in the cloud. And in all these cases, in all the demos I'll be showing you, I'll be using the AWS cloud. So I'm going to show you how to set up this tool, how to set up an EC2 instance, so a computing instance in the AWS cloud. And I'll also be showing you how to run analyses and how we host this. So you will be able to actually access this, the output of this analysis we'll be doing with this tool directly from your computer, from your browser. Finally, to wrap up, I'm going to give an outlook of what is in the cards for cloud computing in terms of bioinformatic analyses. I'm going to point out some interesting trends in cloud computing right now, before we come then to the final slides and you can get some more information about OSTHUS as such, contact information at OSTHUS, and also potential job opportunities and job openings at OSTHUS. All right, so let's jump right in. The big question that many people still have, even after nearly a decade or a bit more of cloud computing, is, but what is the cloud? And the answer to this is very often, well, they're Linux servers. And these servers are distributed globally and rented out for various uses, including things such as file storage and computational resources, which can also be used for bioinformatic analysis, especially in genomics, transcriptomics, and proteomics. Now, to make this presentation a bit more interactive, I have added some questions throughout the presentation. And whenever you see a question pop up, feel free to unmute yourself or to share what you think about that question in the chat. So the first question to all of you is, which cloud providers do you already know? So I think you can just unmute yourself or write in the chat.
Or at least write in the chat.
Yeah, I can see Google and Amazon, AWS and Google, and Azure, AWS, Dropbox, Google. Yeah, so I can see a lot of AWS and Google in there, which are the main ones. All right, so as you have already said, there's a large number of cloud providers. However, there's a smaller number of cloud providers that pretty much dominate much of the market. And as you can see, the main answers that we saw in the chat that were answered mostly, you can also see them in this slide right here. Let me put up the pointer. As you can see, there are 3 big players: AWS, Microsoft Azure, and the Google Cloud, which together make up nearly 60% of all cloud offerings. Now, the remaining 40% are made up by smaller providers, including quite prominent ones, such as Alibaba Cloud, which are also partly, depending on the provider, rapidly growing. But as you can see, AWS is by far the leader and is very popular due to its educational resources, but also due to its competitive pricing. All right, now let me tell you a bit more how the cloud is used in general. Cloud in general is rapidly growing, and there are various different use models, including 3 major ones that I'm going to present right now. In its simplest form, the cloud is used as infrastructure as a service. And in this case, the underlying infrastructure or hardware is provided as a computing resource. Some of the examples that you may know already is the use as customer hosting facing websites or hosting customer facing websites, data storage, backup and recovery, and also high performance computing. The second model that is very popular is the cloud as platform as a service. Now, building on infrastructure as a service, platform as a service, utilizes the underlying infrastructure components, but the hosts also provide, manage, and offer additional features, such as operating systems, for example. And in this case, there's also some use cases, some examples that you may know. A big use case is database hosting, such as the Heroku website, which is extensively used, has also a great free tier. So if you ever want to try out some kind of cloud offering and need a database, Heroku is very much recommended. They have great services there and a great free tier. Then it's also used for business analytics and intelligence, and it's largely used and increasingly used for the Internet of Things. So, you know, all these future movies you see with the fridge talking back to you and telling you that you actually forgot to buy milk. This is all enabled by being hosted in the cloud and by being used in the cloud. Finally, there is software as a service. And software as a service tremendously simplifies life and processes for users, as the cloud providers here host, manage, and offer not only the entire infrastructure, but also complete applications for the users. So software as a service users do not need to install anything. They simply log in to whichever application or service they use and use the provider's application such as it is, with everything, including maintenance, running on the provider's infrastructures. Now, some very prominent use cases for this, which I think most of us have been using extensively in the past and are actually using right now, are Dropbox, which has also already been mentioned, WebEx, and GoToMeetings. All right, now after having an overview of all these cloud computing models, there's the 3 major ones I showed you. There's hybrid versions, and then there's a number of different ones. I would like to tell you what advantages people and companies can get in general by utilizing the cloud. So here I would first like to refer to general advantages that most companies have before going on and specifying how these advantages can be utilized for bioinformatics and for genomic data analysis. So the most often talked about benefit is, of course, scalability. Using cloud computing allows users to rapidly expand or retract computing as well as storage capabilities based on their flexible needs. So if you start a project, you know you need to analyze big data, but you don't know how much exactly you're going to use it, or if your needs are going to expand in the future, this is a great use case for cloud computing. Hand in hand with scalability also comes efficiency and cost efficiency, as users only have to pay for the capabilities that are actually required and used by them. So again, going back to the previous example, you may be doing a project where part of the project requires a lot of computing power, but it's a minor part, which you'll be utilizing maybe 5 or 10% of the total time of the project. So in this case, you would be badly advised to buy these computing resources and have them on site, but instead you can simply request them from the Amazon cloud and use them there. And you're only paying for the time that you use. At the same time, the cloud allows for virtually unlimited resources, like at the snap of a finger. And these resources are accessible at an instant's notice, and they're accessible from anywhere in the world. So especially with the working from home trend that's coming up, especially now after COVID, a lot more people will request working from home, and having the resources they need at their hands is going to be crucial for them to do their work efficiently and correctly, but also for their companies to set up the infrastructure in a way that the company infrastructure and resources can be utilized by the employees now working from everywhere. The next point is accessibility. Now, cloud providers, depending on the model, take care of a big part of accessibility. Resources are usually, they're available at an instant's notice, and as I said, from around the world. Simultaneously, due to this accessibility and resources being outsourced from companies, cloud providers, depending on the model, have an important task. They have to take care of a big part of the data security burden, which previously had to be taken care of by the companies themselves. Now, by making sure that their data and the processes on the cloud provider servers are safe, a big financial burden and also, a burden on employee resources can be taken from individual companies. An example by this, apart from hacker attacks and keeping infrastructure safe from cybersecurity, is, for example, saving data at multiple locations. This is a feat that an individual person or even smaller companies can often not shoulder. An example for this is that cloud providers have multiple resources around the world, and your data, when you work on the cloud, is usually not only saved at one location, but at a geographically separated location too. Meaning, if you have a server, let's say in Japan, and there's a tsunami and takes your server away, so your data server is completely out of it and your data is gone, cloud providers usually have a system set up to have that same data replicated in another zone that will not be affected, just to ensure your data's integrity and data security. Now, finally, and not often mentioned, is reproducibility. This is an advantage that is of special interest in research, including bioinformatics and genomics. And I will be talking about this point in detail on the next slide when I talk about, advantages for bioinformatics in more detail. There's, of course, also some disadvantages. Migrating data operations and general company operations to the cloud is always associated with an initial cost, which many companies, especially smaller companies, are reluctant to take at first. Additionally, you need expertise, so you need specialized employees who know about the cloud and who can take on the responsibility of migrating a company's operations to the cloud. And finally, there's privacy concerns. I think privacy concerns are very important in any talk about bioinformatics and genomics, because when talking about bioinformatics and genomics, we're also always talking about the life science, the biotech, and the pharma industry. Now, these three industries are industries that very often handle very sensitive data that cannot be disclosed at any cost, such as trial data, but also patient data. So there's a big privacy concern, and the fact that even if the cloud takes care of data security to a certain extent, the data is on remote servers that do not belong to the company, and where the infrastructure, so the hardware, is often shared by more than one customer, that can raise privacy concerns that make a lot of pharma industry and biotech companies reluctant to actually move all of their operations to the cloud just yet. Okay, in general, apart from the disadvantages, the advantages are usually able to give companies a competitive edge because they are able to be much more flexible in their operations. They save a lot of money and they outsource a lot of the issues that are problematic for smaller companies or even sometimes for larger companies. Now, from that general overview of the advantages, I would like to go on to the advantages, how they translate into genomics, and look at each and every one of these advantages in a bioinformatics specific way. But first, again, as we're from different backgrounds and have participants from different backgrounds, I would like to give you some background on what's occurring right now in the genomic fields. So in the genomic fields, one thing that has happened over the last years and decades is that sequencing costs for genomic, transcriptomics, and proteomic data has been steadily and drastically decreasing over the last years and decade. Now, to put these decrease into perspective for you, I would like to give you an example. And the example is of the Human Genome Project. The Human Genome Project was a project that was started in 1990, and it was aimed at sequencing the complete human genome, meaning to find out which sequence the genome of a human has, which back then we didn't know. This project was estimated to run for 20 years. And in the end, thanks to technological advances, including or especially in sequencing technologies, the project was completed in only 13 years, and gaining information on this first human genome cost a grand total of $2.4 billion. This should be dollars, not euros. Now, in comparison, and to set things into perspective, today sequencing any human genome costs only around $900 or euros and takes just under a day. So I'm sure you can see the tremendous advances we have made here. And the impact is not only one for researchers in academia, but I'm sure many of you have heard or have maybe even used some of these sequencing services, such as Ancestry or 23andMe, to learn more about your personal DNA. Now, these are services that are made possible only thanks to advances and decreasing costs in sequencing technologies. And with these new services popping up all over the place in combination with decreasing costs in general, DNA sequencing is rapidly becoming more affordable and also more accessible for many people, in addition to researchers and companies. All of this now leads to an explosion of omics data, with omics data being genomics, transcriptomics, and proteomics. Now, with this in mind, I would like to put another question up for discussion. And there's no correct answer here, so please feel free to unmute so we can have a short back and forth discussion. The question would be, based on the advantages that we just talked about or that I just showed you, and seeing the decrease in cost and exploding growth of sequencing data, what immediate advantages comes to mind for you?
If I understood correctly, it's speed. Yeah.
Yeah, speed is definitely one of them. So we can process and analyze our genomic data a lot faster. Yeah, and cost definitely. Also seeing how usually getting a certain speed, computational power to get this speed, requires much more expensive computational resources that many smaller companies and also researchers themselves cannot shoulder. By going to the cloud, the costs, of course, significantly decrease, and you get both reduced cost and larger speed.
Sounds a bit unbelievable from the project management perspective, you know? Normally it doesn't go this way.
Yeah, in this case it does. So you get the best of both worlds. Anyone else, feel free to unmute yourself and share your thoughts on what could be the benefits of cloud computing with these two points in mind, for example.
I think probably one of the advantages might also be that just with the decreasing cost, you have much more data, and you can actually have much more references to data taken all around the world. With, for example, I think with this Ancestry project, it relies heavily that all around the world you actually have genomes from all the different people. So without the decrease in cost, this would not be possible to have a database of this kind.
Yeah, I think that's a very important point, and one that's often overlooked too in talking about advantages is scientific collaboration. Yeah, I think we're producing so much large data right now. Yeah.
Yeah, that's exactly what I wanted to say, that it's scientific collaboration between different countries, because without that cloud opportunities, that would be impossible just to send emails with Excel tables or what.
Yeah. Yeah, exactly. That's a very important point. I mean, I think you had a background in you're a physicist, right?
Physics, yeah, and a little bit plant research.
Yeah, so you definitely know about big data. You know how big these files are. Bioinformatics often works with big files, big genomic files. They have a lot of, they're very large files. And as you said, you cannot easily send them by email. So being able to put them on the cloud definitely confers one of the biggest benefits. And that again plays into what Sebastian, I think, said, that once you have a way to share the data, other people can participate in your research and to find a lot more valuable insights than just only one person from one limited data set. So you can actually make connection. And this is, I think, also one of the big advantages of big data, putting it all together, and the benefit you get from it increases exponentially.
I could also imagine that if you put some type of software on the cloud, that if all the data are processed in a similar fashion, then the reproducibility could also generally increase. And if the data is treated the same way for every customer, so to say, then it's also more likely that it's better quality of data.
Yeah, that's a very, very good point. I'm actually impressed by the quality of results, because you basically taken all my points from the next slide away already. But yeah, reproducibility is a huge one. I mean, on one hand for customers, but also for the scientific community, right? Have you worked with bioinformatics?
No, but I know what happens if you have data and you have two different types of scripts. You can get very different results. So yeah.
Yeah, exactly. That's the point exactly, that especially in bioinformatics, reproducibility is important. I mean, in science in general, because you have to be able to reproduce results, to peer review them, and have the scientific process going on. But for bioinformatics, it's especially important because you have all these tools with all these parameters. So yes, reproducibility is definitely a big one.
Another point.
Yeah.
I have one point to make. Like, sometimes we use different algorithms or different ways to manipulate the data. So we can even do is parallel computing on those on those cloud platforms, so that we save time at the same time cost.
Yeah, exactly. That plays into scalability and cost efficiency. That yes, you can easily do parallel computing, perform parallel computing to try out different scripts on your data. Yes.
I also wanted to say that just the scope of analysis has expanded hugely. The type of analysis that we used to do before, or the type of analysis that we can do with this data relatively cheaply available nowadays, is much more and much more comprehensive than what was possible before.
Yeah, that's another important point. I mean, we've had a lot of data before and we had a lot of knowledge. However, we didn't have the computing resources to perform a lot of analyses that give us all these important insights that we've been generating in science, right? So I think there's also a very valuable point here, that by increasing our computing capabilities and generally just having technological advancement, you can utilize the data maybe that you already had even in a completely different way that again multiplies the benefit of the results that you get back.
Gabriela, it actually makes me wonder, because I'm not from bioinformatics background. So this question is for you, Gabriel, and perhaps Nikhil as well. Yeah. Because in bioinformatics, like genome sequence and so on, we have such huge data sets. How exactly were these data sets shared before cloud came into picture?
Well, they were often not, or on a hard drive, or yeah, it depends. I mean, this field is moving very fast, right? So what you're describing is already before my time in science, basically. But I remember when I actually started on my PhD, sometimes that was exactly the problem. We had some data like, how exactly do we share it? A hard drive is often not enough. So it was a lot of hard drives back and forth, still checking data integrity. So yeah, you were very limited by this issue of data sharing.
I have worked with colleagues who have worked on yeast genomes or bacterial genomes, and they used to carry set of hard drives from one lab to another lab and then put it in other computers and then copy the files. So that is how it was shared physically.
Right.
I also don't know it for bioinformatics, but if you do it for neuroscience, for example, I think also just the solution would be there was no sharing. That was not really what you would do. I think that's also more a newer topic, that labs are actually more free and open with their data that they actually shared. Before they were like more hoarding it and really wanted to keep it all for themselves.
Yeah, totally. I think there's a big shift in mindset about open data, open science sharing. But yeah, that's exactly it. A lot of labs were reluctant to share their data, didn't want to share it, or didn't have a way to share it. However, today, there's not only a shift in mindset for many people, but there's also a shift in policy. Many publishers, many journals actually require you to publish your big data or to host it on some kind of repository before they even accept you for publication today. So there's also a shift of thinking there. All right. So anyone wants to add anything to this already very fruitful discussion? All right. If not, then we can continue. Yes. So a lot of points that we have discussed, you will hear me repeat now because we had tremendously good points. I'm very impressed by the quality of the short discussion that we had. Some points that we have included storage, computing power, but also sharing of data, and just the capabilities of analyses that are enabled by stronger computing powers and just technological advances. So let's see now in details how these advantages that are already presented before actually translate into bioinformatics specific advantages. I think we can start with scalability, which enables bioinformatic analysis and also research efforts to dynamically scale with changing needs. Now, taking the current pandemic as an example, we can say, for example, databases or websites hosting COVID data went from, well, relatively a smaller research area or niche to a massive research field in the, I don't want to say in a matter of hours, but definitely days. And with that came also the demand on online resources, which got multiplied drastically. So imagine you were hosting a database for, let's say, COVID-specific data. Before, sometimes during the day, some demands would trickle in, but after the pandemic started, it would be a flood. So this led to that many local servers or even servers from smaller companies could have easily crashed under this new demand. However, if you had servers that were hosted on cloud resources, these resources can easily be set to expand either vertically, meaning to recruit a larger computing instance, or horizontally, meaning it automatically recruits more computing instances, depending on the demand that you get. And of course, this scaling is not only useful for spikes in websites and database demand, but it's also useful for analysis. So labs that usually did a moderate amount of analysis, let's say again, on our COVID example, would have had a drastic spike in demand on computing resources to actually analyze all the samples that they get for analysis. And in the case of cloud computings, this demand could easily have been met by recruiting more instances or larger instances from the cloud. Now, the nice thing about this is many cloud providers have features built in where you have some instances, you buy these or rent these for your baseline. However, the system is smart enough to decide when it's going to scale up and rent out a second server or a bigger instance if the infrastructure sees that your needs are actually increasing and you're using more data than you actually currently can with the resources that you currently rent out. The next point is storage. And before looking at storage in detail, first, another question. Now, this is a multiple choice, just for everyone to grasp the scope of the storage issue in genomics. In order to grasp the scope, I would like everyone to answer the multiple choice that Sujit is going to open up for voting in a second. What is the size of a fully sequenced human genome? Now you're going to see a slide with 4 options, and feel free to just go ahead and click the option that you think most accurate. So we're asking here about the size of one fully sequenced human genome. I'm going to give this a minute or so. There's no wrong answer, and well, there's 3 wrong answers, but so it's not going to show who's answering what. So feel free to answer and guess if you don't know. I think we're given another 10 to 15 seconds and then look at the results. Okay, let's end the poll and see what kind of results we got. So I'm sharing the results right now. Can you see? Yes, okay, great. So you can see we had 4 answers: 100 MB, 1 GB, 200 GB, or 1 terabyte. And you can see that our answers varied quite a lot. There's answers as small as 1 GB. So, okay, no one actually thought that a human genome could have enough space to live on 100 MB. But 1 GB was selected 3 times, and 1 TB was just selected twice. The actual answer is 200 GB. So 1 human genome, let's go back to the presentation. Sujit, could you please cancel the poll so it's not shown anymore? Great, thank you. Yeah, so let's go back to the slide. The right answer is 200 GBs. So the size of one fully sequenced human genome is approximately 200 GBs. That also means that on 1 terabyte of storage, you can only host about 5 full human genomes. And in preparation to this meetup session and presentation, I actually looked up the cost for the largest external PC hard drive I could find on Amazon. And the cost and size is not pretty. So you can see that the largest, hard drive for a PC I could find is 16 terabyte. And the price tag is currently a very respectable, nearly $500. So you can also see the size of this hard drive here. It's not portable at all anymore, so it's quite large. So this is not sustainable if you're a researcher in human genomes to fill up your home with these hard drives, you won't really get that far. Now, a person or research company researching human genomes will frequently sequence human genomes, and they will need a multiple of this size that we can see right here in order to perform adequate research. So in summary,
have a question in between, if this is okay.
Yeah, sure.
I was wondering about these 200 gigabytes. What is there included? Are this just the four letters which make up the DNA over and over repeated? So like we have 2 bits, and every combination of these 2 bits are representing 1 letter, and then the data is just a string of 4 letters? Or is there also included some sequencing information, or what is actually stored in these 200 gigabytes?
Well, it usually depends on the sequencer, but largely we do have, I want to say, nearly only the sequence. So you have the sequence, and apart from the sequence, you usually have some base calling quality information. So you have a sequencer that tells you what sequence for the different reads you find, and each of these bases are called, and they have a certain quality score associated with them. And that quality score is that quality score is usually included in that file. But basically, you have the sequencing information and some minor information regarding the sequence, so the sequencing itself and the quality.
Wow. Okay. So the 200 gigabytes is
they're really that big.
Oh wow. Okay. And another question following up from there, for the compression of these files, I think somewhere in my head there's the information that the human DNA is very, very similar between each human. So could one make a compression algorithm which just has a default human DNA in it, and then also only print the parts of the DNA that vary?
Yeah, you could, but then you wouldn't need a sequencer, because that's already that's already researched. So the regular human DNA, the reference human DNA, you can find it online. Now, the interest many researchers have is actually what you just said, the differences between human DNA, which are usually SNPs, single nucleotide polymorphisms. So it's usually 1 or 2 bases out of a section of million and billion bases that changes, and you have to find it. So these files are usually FASTQ files. They're usually zipped, but you don't lose any information. So it's not a lossy type of compression. And the reason it can usually not be is because you would have to perform analyses on the reads before actually knowing which of the read bases are different from the standard human genome, right? Which would be mutations. So I think doing this type of compression that you actually suggesting defies the purpose, because you have to do the analysis before you actually compress it, because you need to know which bases are mutations.
True. I think my idea for this compression was more like for sharing files when you don't want to carry around huge hard drives. Then you could maybe share these informations in a smaller way. But sure, you have to have them once in the bigger format.
Yeah, exactly. Also, these files are frequently zipped, but it usually doesn't help that much. Like you get some compression, but it's not. You won't get a 1 or 2 gig file from a 200 gig file.
Yeah. Okay. Thanks for the answers.
Welcome. Any other questions? Okay. So where was I? Yes, I was talking about storage, and I wanted to show you a quote that I find quite impressive. The quote is, raw sequencing data has been doubling in size every 18 months. So this means that all our sequencing data from years and decades of research and sequencing will double. So that amount we already have for years and decades will double within the next 1.5 years. And it would double again in the next 1.5 years after that, and so on and so forth. So I think if you just calculate it in your mind for once, you can start perceiving the sheer scope of data that we're actually talking about and that needs to be handled in genomic and bioinformatic research. So using cloud for storage is one of the big parts or benefit that enables genomic research as a whole by facilitating data storage of this big data, like we talked about before, for various reasons, also for sharing and collaboration, which I'm going to talk about in a second. But yes, one of the big breakthroughs in genomics is actually that we have a place to store all this data. We can use it, because producing is one thing, using and getting valuable insight is the important part, and this is being facilitated by the storage possibilities in the cloud. Okay, the next point is cost efficiency. On one hand, for storage, as we just saw, this can become very expensive very fast, but also for computing resources. So cost efficiency for both storage and computing resources. In the cloud, researchers only pay for the resources that are actually used. And in bioinformatic, analyses are usually not run to the same extent day round and year round as in other industries. There are usually some peak hours that often coincide with working hours, and then there's some off hours. Additionally, in cloud bioinformatic computing, you have some types of analyses which require very much storage and many computing resources. And then you have many types of analyses which are performed quite often, such as tertiary analyses, which usually do not need all that much storage or computing power. So by using cloud computing, researchers and companies can maximize the bang they get for their buck, as they only have to pay for the resources they use, for the time they use it, and at the moment that they use it. So they can easily perform an analysis requiring a high-performing computer, and the next minute or the next day use something much smaller, like at the size of a personal computer, and they only have to pay it while they use it. Now, in that regards, unlimited resources is also important. As you have seen, genomic analysis requires a lot of RAM, but also a lot of storage. So having unlimited, in quotes, unlimited resources available to do your research is really a lifesaver. Accessibility is the next point, and accessibility is especially important in scientific research, including bioinformatics, as scientific collaborations and knowledge sharing is one of the big drivers and also accelerators of scientific advancement. I think we talked about it, and two of you mentioned it during our discussions a few minutes ago, but being able to host and also to share information in the cloud and have colleagues from around the world being able to actually access that information from anywhere and anytime is invaluable to this end. This is especially true for big data, such as genomic data, that cannot simply or easily be shared by other ways, such as email. So that was also a comment from before. We cannot easily share these data files, this big data, by email. So having this other way available is really useful. So the accessibility that the cloud provides definitely also facilitates and it enables efficient collaboration, which drives bioinformatic insights and scientific insights in the genomic fields. Having accessible data also means that data security is essential, not only when working with colleagues, but especially in regards to open source projects and data. Now, hosting data on the cloud transfers a large portion of data security responsibilities to the cloud providers, as mentioned before. This can be an advantage, but it can also be a disadvantage, especially when working with highly sensitive or classified data, such as in the pharma field, for example. Many pharma companies work with data that cannot, under any circumstances, be disclosed. Now, one final advantage of doing bioinformatics in the cloud is the potential for reproducibility. I think Sebastian mentioned that before. And this is one point that I cannot stress enough, and it's often not considered enough, especially in research. Now, reproducibility is one of the pillars of scientific research and one of the most crucial elements, especially in bioinformatics. And in bioinformatics, that is especially the case because we deal with a tremendous number of different tools with different parameters and on different systems. So there's not unlimited, but very, very, very many variables. And bioinformatic analysis workflows can easily be packaged up, for example, in containers like a Docker. And in these Dockers, where all the parameters and variables are set in a certain way. So you define them, you put them on the Docker, and then you transfer to the cloud so that other people can use it. And once that's done, colleagues and researchers around the world can access that exact workflow to accurately reproduce your analyses. So they don't have to do any guesswork or get any mistakes or differences due to very simple differences in your workflow, your pipeline. Now, one of the currently biggest challenges of bioinformatics is that workflows are often not reproducible. And that's due to a huge number of, as I said, potentially varying parameters and systems. So this challenge could therefore be remedied by using access to the cloud and packaging your workflows and putting them up. Now, in my eyes, this point is the most overlooked advantage that we can derive from using cloud computing in bioinformatics and also in genomics. Now, all taken together, these advantages lead to results too. So on one hand, we have fast results. As we mentioned before, we also have lower costs. So fast results at lower costs, which means we can produce many more results in the same time frame. And that means a lower time to market. Or as the PhD students here will know, a lower time to publication, which can actually be a lifesaver as a PhD student. So yeah, using the clouds saves lives, if I want to exaggerate it. All right, so with that theoretical background in mind, let's move on to something a bit more practical. Now we're about halfway through this presentation. In the next 3 slides, I'm going to present some IT architecture. So I'm going to show you some cloud setups, how to use first in general and then also in bioinformatics. And after these IT architectures, I'm going to show you the more practical part of the course. So I'm going to introduce a bioinformatic tool, and then I'm going to show you how it's hosted in the cloud, and you're going to access that tool by yourself using a link or IP address that I provide. Okay, let me first now give an overview of a general IT architecture, such as it is used in the cloud. In my example, as mentioned before, I will be talking and using AWS as a provider. Now, a typical architecture will always start with data that you can see here on the left-hand side. And you can also see that there are a large number of different data producing sources. In the first step, that data is migrated to the cloud right here. And this data ingestion, as it's called, can happen in a number of different ways and also using different tools and services. But the aim of this step is always to load the desired data that was previously produced into the cloud infrastructure at first. Then from here, the data is processed and cataloged and stored in a more permanent location. In case of AWS, it would be, for example, an S3 bucket. Now, from this location, the data can be requested and accessed by various tools to perform different types of transformation and analyses on the data. And the data itself and the analysis results can then be accessed either by researchers, bioinformaticians, or even follow-up programs or other entities, given the right permissions. And additional, also this data, so uploading, downloading, or changing the data or results of analysis can additionally trigger automated workflows, as you can see down here. So this is just a rough workflow of an RT architecture as it can exist in the cloud. But now let me show you how we can tweak these architectures for bioinformatic purposes. So on one hand, we can build an architecture for genomic data management. Now in this scenario, we also start with our data sources. We basically always start with the data sources. And in this case, these data sources can be sequencers, some manually inputted data by the technician, or also clinical data, like you can see down here. Now, after migration to the cloud, the data is initially stored in a central location from which it can either be accessed directly for analyses or processing purposes in an active manner. So this is active data. Or if you're not planning to use the data that much, or if it's not used as much in general, the data can instead be moved to a less active location for longer term storage. Now, this can be done using something called lifecycle policies. As you have seen, genomic data is quite large, and keeping it saved and stored at a location where it can be retrieved at a moment's notice can be quite expensive even in the cloud. So this is why many providers introduce lifecycle policies, and lifecycle policies act on inactive data so that you can decide when to move inactive data. So after how long you can move inactive data to a deeper location, so to an inactive data location, where it's still stored safely, but where retrieval can take much longer. So as an example, if you save your data in an active location, you can retrieve it in a matter of seconds or milliseconds. If you move it to a less active location, such as Amazon S3 Glacier, it can instead take up to 5 minutes or 10 minutes, depending on what you want. However, due to that time lag that you have to retrieve your data, you also pay less money. Now, this is especially useful for data that has to be kept, for example, for monitoring or documenting purposes, but that is not actively worked on anymore. Okay. So another example is data aggregation. Now, while the amounts of genomic data are exploding, this data itself is usually not very useful in and of itself. Now, many of you will gasp, especially after having talked so much about genomic data, but what makes genomic data really interesting and really useful is the metadata associated with it. Now, a genome sequence itself is not of much use if we don't know what organism it's from, where and when the sample was taken, if it was taken from a control group or from an intervention subject, let's say in case of the clinical studies and so on. So linking our genomic or sequence data with relevant metadata, which are often available in tabular forms such as CSV files or Excel files, significantly increases the insights that we can obtain from said data. Now, using the cloud for this purpose facilitates this goal a lot. So we can set up a management system that will keep everything organized for us, and that can expand or draw connections between old and new data rapidly. So you can see here data including sequencing data and metadata. It's loaded up here. And in here, you can create the connections that you really need to work with your data. Especially, you can connect your metadata and say, okay, this metadata corresponds to this sequencing data. Now, we can also set up policies to determine who can access which data and when. But the main point here is that having catalogs and integrating our genomic data in this way can facilitate many types of analysis, especially tertiary analysis, where we need a lot of metadata to start with. Okay, with this short journey into the world of IT architectures, I would like now to come to the practical part of this presentation. So in this part, I'm going to show you the tool NextStrain. So first, I'm going to show it on the website itself. And then in the next slide, which is, we have only 3 slides left. So in the next slide, I'm going to show you how I set up this tool in the AWS cloud. So how I installed it, how I ran the analysis, and then how I hosted the output on a web server. All right, let me just pull up and share this screen. NextStrain. All right, can you let me know when the screen changes for you?
Okay. Yeah.
Yeah, okay, but I think it hasn't loaded yet. Let me open a new tab for this. Oh, now you can see it. Okay, can you see it?
Yeah.
So you should see some kind of phylogenetic trees right now. Yeah, connection seems to be a bit slow, so it failed to fetch frequencies, and now it's gone again, but it should be back in a second. All right. So what you can see on this screen right now is the tool I just mentioned, NextStrain, which is used for creating interactive phylogenetic trees. So you can see, and I'm going to be very careful with this because our connection is slow. You can see if we zoom over it, you have a phylogenetic tree regarding the novel coronavirus, and you can see it on a timeline. So you can see the first samples taken in December of 2019 up to today, so June 2021, and you can see how these samples differ in mutations from the original sample taken. So if you hover over these different points, you can see the location of nucleotide mutations in comparison to the mutation before it. You can additionally also click on these points and it's going to zoom in. I clicked, but it's quite slow, so it will take a while. Yes, so we'll zoom in. It will show you on this map where the sample was taken, and it will pop up some additional information about this sample, including things such as the originating lab, but also the publication and the GIS8 number. So there's a lot of information and there's a lot of room for customization. Now let me go back to the tree right here. Additionally, you can do a bunch of the layout of this analysis by clicking on radial, for example. And this can be important, for example, if you plan to publish such types of data. Some journals have strong rules for how the graph should actually look. So that's some of the things that you can actually do. And then you have a bunch of different features. So basically everything surrounding the information, the mutations of this coronavirus right here. So now that you know how this tool should look like, let's go back to the presentation. And let me tell you how I ran this analysis, installed this tool, and hosted the output on the AWS cloud so that you will be able to see it in a second. So first, I'm going to show you some screenshots about what I did. In the first step, after going into the cloud, in my case it was AWS, you log in into your account, you have to choose a computational instance that is adequate for your task in size, but also in speed and processing power, and you have to initiate a computational instance. So before actually choosing the size, you have to choose what type of instance you want to use. You can see here a bunch of different Linux distributions like Red Hat, you have Amazon Linux and also Ubuntu. So in my case, I choose Amazon Linux 2. And then the next step, you go into that instance and you check what types of instances are available. In my case, and for the analysis with NextTrain that I wanted to perform, I needed an extra large unit with 4 CPUs and 16 gig of RAM. So you can see this is quite flexible here. You can really use the smallest instance, which only has 2.5 gig, up to the larger ones of 32 and even larger if we scroll down. So after choosing this instance, you go ahead and you have to configure something called security groups. Now here in the security groups is when and where you actually decide who can have access to your instance and how. In my case, I needed to SSH into the instance. So I needed to go into the computer to be able to make changes in the computer itself. But I also wanted everyone to be able to see my output on a web page. So in this case, HTTP. So this is basically the port for the web server. In this case, or first, by standard, this is set to my personal IP so that no one else but me can actually access my EC2 machine, so my cloud server. But I can easily change it. Oh, where is it? Oh, yeah, down here. So you can see that I changed it from a personal IP to the complete IP range. So this means that it changed from, okay, only I can see my server on the website to, okay, everyone can see the server on the website. And this is because I want you all to access this website. After all of this is done and we chose the instance and we configured the instance, you can go into your instance. So you can see this looks just like a regular terminal. I'm sure many of you have worked with Linux. So you can connect to your instance, for example, via SSH right here. And once you're in your instance, it looks just like a regular Linux server. And just like a regular Linux server, you can also perform everything that you do on a Linux server, meaning you can install all the necessary tools. In this case, I installed NextTrain and Docker because I needed them. You can run the analyses. So in our case, again, I downloaded some sample data of the Zika virus. And performed. So I created the tree that you before saw with COVID, but only with the Zika virus. And finally, after installing and running analyses, you can take the output and you can host that output, for example, as an interactive dashboard on a website. Additional to all this, you have an IP address that is connected with your EC2 instance, but you can choose the port where your output is going to be hosted. So in our case, that's port 8080 because I chose it. So I'm going to copy this. Or Sujit, could you copy this and put it in the comments so everyone can click on it and explore it for themselves?
Can I copy? Okay, yeah, wait, I must be having the presentation. Yeah, 1 second.
Okay.
Sorry, I don't.
No, okay.
Yeah.
Then let me just type it here maybe. So everyone can just click on it and go to this location. It's 482, or it is 8080, and it's Zika. All right, so I put the IP address and the location into the chat right now. So if you just want to click on it, and I'm not trying to steal your personal information, so it's really safe to click on that link. So we'll have to copy and paste it into the website. And while you do this, for the people who cannot do it or who don't want to do it, I'm going to show the output here. So I'm going to give you about a minute to get there and explore a bit before I'm continuing the presentation to show you interactively what can be seen on the website. Once you're on the website, give a short feedback, either unmute yourself or just write in the chat that you were able to access it, so I know when we can continue. Okay, works for Sebastian, good. Yeah, Philip too. Parna can also access it, and Nikhil. Yeah, okay. So I think many of you, or I would even say most of you, are able to access the website. And what you can see here is the output of the tool that I previously showed you on the website. However, now I installed it on our AWS instance. I ran the analysis there, and now I'm hosting the output of this analysis on the AWS cloud. So what you can see here is a phylogenetic tree for the Zika virus. And you can see there's a lot of a lot of customization there. On one hand, I changed the title so that we know it's special for the OSTHUS Meetup. There's also a link to the person who maintained it. Right now, that link is not going to me. I didn't personalize where it's going to, but you can see that it's very similar to what we see on the Nextstream website. And similar to Nextstream website, you can actually click on the different links. It will zoom in. It will give you more information. You can reset the layout. It will show you the map. Currently, it's not showing the map, but it's, however, showing the connections, the geographic connections between the individual samples. You can scroll down and you can actually select specific samples. So if you click, it will only show you this one, in this case, Venezuela. And I'm choosing Venezuela not without some back thoughts, or I gave it some thought, because if you actually zoom in and click on this, you can see that I, in this case, personalized the title. So usually you have the article title here. In my case, I personalized it to say, "Hi Meetup," and customized for demonstration purposes only. This is simply to show you that this is a tool that's highly customizable, and that all the changes that you actually make, the output that you have after your analysis, will still show up in on the front end of your website so that other people can see it. Yeah, so I think I'll give you 2 minutes or a minute to play around with this, and then I'll come to the final slide of the presentation.
I would again have a question.
Yeah, please go ahead.
These connections between these dots, do they refer to the genetic tree on the left side? Or what?
Oh, you mean these here, the transmissions here?
Yes.
Yes, they are. Like, usually it should be a map. You should see the word map under it. Mm-hmm. So this would, for example, be the samples in the US. This would be the sample Dominican Republic, Venezuela, and so on. However, for some reason, I think the connection is slow. It's not showing the underlying map. So there should be a word map under it, and the point should be on top of the locations where the samples were taken.
And the connection between 2 points, what does the connection indicate?
Mm-hmm. It's relatedness. So if you can see here, let me actually show you in a different manner. So you can also change as shown before. So what you can see now here is you can see a timeline from 2014 to 2017.
Mm-hmm.
And you can see something called divergence up here on the left-hand side, so on the y-axis.
Mm-hmm.
And what this is, so this analysis is built on a reference genome. So you have a reference genome for Zika. And then you actually calculate the divergence for each of these samples, for each of the Zika genomes, compared to your reference genome. And you can see samples taken very early, they don't really differ much. They're pretty much similar to the reference genome, but the later you go, the more mutations you have in the genome and the more difference, the more divergent your samples and your Zika genomes actually are from the reference genome. So what these lines show is the extent of relatedness. Or as you can see here, they're basically these lines only overlaid on a geographic map.
Yeah, okay. So clustered against geographic and against similarity in the genome.
Exactly. So in other words, you could say very carefully that this is likely, it's likely the route this virus traveled and how it mutated. So from here to there and so on.
Okay, thanks.
You're welcome.
I have a question. What is the maximum storage that a cloud has in general?
Sorry, could you repeat this? Your audio is a bit bad on my end.
Yeah. What is the maximum storage that a cloud has in general?
The max of the whole cloud? Do you mean of my AWS instance? Do you mean of a provider? You mean of the cloud in general?
Cloud in general.
Okay, I would say that's very big. I would have to look that up.
No, I just.
But I would say very large.
Yeah, if there's some data which is very huge and no one is doing any research on that data, and how important is to have that data in the cloud. Like suppose there's a pandemic like Corona, like COVID, and which is ended by next year, and no one wants to access the data after 20 years or something.
Yeah, the exact size I couldn't tell you. I think as an individual person or even company, you could add unlimited data. Would be virtually impossible for you to fill up the cloud. But of course, it's not unlimited. I said unlimited before in quotes. The exact size, I don't actually know. I actually just Googled it while answering your question, and the only thing I found was the size of the market value. So the size of the market value is about 397 billion US dollars of the complete cloud, but the actual size of the cloud, I don't know. And I'm not sure if anyone would know because a lot of this information, I guess, the cloud providers always keep private. So I'm not sure all cloud providers would actually output the numbers of how much.
Maybe I can pitch in here. Yeah. See, in theory, it's unlimited, right? But we all know it has to be some big number. And the point is, all these cloud providers like Google Cloud provide platform, or even AWS or Azure or any provider, they are ever expanding. So companies like Google, Amazon, Microsoft, they are creating new data centers where they have huge storage capacities. You might have heard about even it's like underneath ocean and so on. So as we talk, the cloud storage is expanding. Of course, it's a huge number, but the number is like constantly expanding. So it's difficult to keep a track.
Yeah, I'm just wondered like the amount of data is increasing, and will we be able to hold the data in future? Like, will the cloud will be able to hold that much amount of data? Yeah, no, but it's okay. Yeah, thanks.
Yeah, Parna, I think about hosting the data at this moment, as Sujit said, I mean, it's always expanding. So the expanding of the cloud providers' capabilities are probably going to keep pace, or hopefully with the necessities of the world.
Harsh has the answer, as always. Currently, if you Google, it says currently it is 295 billion gigabytes.
Okay, that's huge.
Yeah.
That is, that's tremendous. But yeah, very, very, very large, definitely. Okay, then let's go back to the presentation. Can you see my presentation screen again?
Yeah.
Okay, great. So this was the URL that I just showed you and that you just explored a bit on your own. However, using the cloud and hosting any kind of output information or website, interactive dashboard on the cloud doesn't always have to have such an ugly output. we actually converted this IP address, or we connected this IP address to a domain name at our OSTHUS domain. And usually if you go to this link right here, you should see the same output as if you go to this IP address right here under this port and this path. However, this is currently not working because I just tried it before this presentation, it somehow broke down. But in general, the point here is using the cloud, you do not have to use the server's IP address. You can also make it prettier and more user-friendly by using a domain name and linking it to it. All right, so with that presentation, I would like to go back to the main presentation. We've arrived at the final slide. And for this part of the presentation, I would like to give you a brief outlook of what's in the card for bioinformatics and genomic analysis and the cloud, and to point out some of the more interesting trends. I think one of the most impressive things we've talked about is the exploding data. There's a tremendous data explosion going on right now, and it's driven largely by increased sequencing technologies, but also by capabilities in the clouds. This in turn is driven by increasingly competitive pricing in sequencing and also cloud computing. So more and more people, researchers and institute can actually afford to migrate their operations to the cloud. Having these things in mind and knowing that, we also always have to think about security standards, because the cloud is online and there's a lot of cyber threats online. Many cloud providers are actually currently in a battle with not only with hackers, but also with other cyber threats to keep or to maintain security standards that will keep the integrity of the data of their clients and customers safe. So this is going to be one of the main battles that have to be fought in order to actually get the most benefit and continue to keep the cloud a safe place. One other trend that's very much driving the migration to the cloud and also the benefits from the cloud is an increasingly holistic view of the scientific process. And by holistic, I by no means mean esoteric or anything religious. I simply mean the integration of data forms from different sources. So this on one hand can be what we talked about before already, where we integrate our data, for example, sequencing data with relevant metadata, but also where we integrate and connect different types of data, different sequences taken around the world with each other, because in combination, when they are connected, metadata and different types of data usually render a much higher return, have a much higher value than isolated by itself. Additionally, the integration of data from various sources doesn't only mean data itself, so metadata and different sequences from different labs, but it also means different types of, for example, sequencing data. So especially in research, in genomic research, we've been seeing a trend where we go towards the path where we not only analyze the genomic data of something, but we at the same time look into and analyze the transcriptomic data and the proteomic data, so that we get a fuller, more holistic picture of what's going on in our sample of interest or subject of interest. Finally, there's been a rapidly increasing awareness of the value of data. While oil was the hottest commodity of the last century and water is very important in this century, data is close to giving water a run for its money. And the awareness of data as the new oil is actually rapidly increasing. And not only people, but also companies are seeing the value of data. And not only, again, the data itself, like sequencing data, but in combination with metadata, which always requires to correctly catalog and tag and store your data so you can find it back at the right time when you need it. This finding the data back at the right time and connecting it with different types of data is also important for the final point here on the slides, which is AI, so artificial intelligence and machine learning, which will have tremendous benefits from using open data sources, all the big data we're putting on the cloud that is produced in our data explosion. Finally, as a one-line statement, I can see tremendous potential for the public as well as for the private sector in the further development of cloud computing, especially as we extensively talked about for bioinformatic and genomic data analyses. And I think the insights we'll be gaining in the future from these tremendous amount of data that are produced are only going to increase even more as we connect things more, as the cloud matures, and as data is more freely shared between entities, so that a larger number of people can actually gain benefits from a data set as opposed to it being hosted on one lab, on one computer, where only the one researcher who's working on it can actually access it. All right, so with that, I would like to finish this presentation. I would like to thank you all very, very much for your attention. I hope you liked the overview. I hope you liked the presentation. And